That is the definition of rolling without slip. But for a cone of this nature, I'm going to have a whole line of points which are in contact with the xy plane at any given instant in time. And the locus of all of these points is called an instantaneous line of contact. It's instantaneous because at the next instant another line comes and contacts the cone, xy plane. Okay? So rolling without slip implies, for our situation, the line OC is an instantaneous line of contact which tells me that the velocity of any point on this line OC at any given instant in time is 0, or at that given instant in time is 0. So this means that velocity of all points on OC is 0 at that instant. Make sense to everybody? This line OC is going to keep changing, right? At the next instant, there is some other line on the cone which is going to come in contact with the surface. It's not like the same line is going to sit there and do something. The other piece of information that's given in this problem is the following. The rate of rotation of this instantaneous line of contact of this, I want to call it as ICL, instantaneous, ILC, I guess, instantaneous line of contact, ILC. So that's my shorthand notation, I just don't want to write it out. Instantaneous line of contact is omega, some rate omega. About which axis do you think this is going to be? About the z axis, right? Absolutely. So that's another piece of information that we are given. What am I supposed to do in this problem? Obtain the angular velocity of the cone related to the plane F1, which means obtain the angular velocity of the body. So we call the cone as the body here. So this is essentially omega of the body with respect to F1. When the instantaneous line of contact is aligned with the y-axis. Make sense to everybody? So this keeps changing, right? The angular velocity is going to be different at different instances in time. So at this instant in time, when the line of contact is aligned with the y-axis, what is the angular velocity of the cone? Just so that this is a much more simpler situation to visualize. Nothing, not that the procedure is different if I have to look at a different instant in time. It's the same thing that is going to follow. All right. Now, what we want to do is we want to set up 3 coordinate frames. We already have the first one set up, which is the frame F1, which is represented by I, J, and K. Right? So here, this is frame F1, X, Y, Z, frame F1. Then you see that I can attach to this line of contact at any given instant in time. Right? So at any given instant in time, so suppose I extend this here, at this given instant in time the line of contact is sitting here. At the next instant in time, what's the line of contact going to do? It's probably going to be somewhere, here. At the next instant in time, if this is the plane that I'm looking at, the line of contact will be somewhere there. The next instant in time, line of contact will be somewhere here. So this line is rotating about the z-axis at a rate of omega. Right, so this is the line OC. At the next instant in time, this is some line OC1 because the next point is coming in contact. At some other instant in time, OC2, OC3, and so on. And so if I attach a coordinate frame to this line OC, what are the potential directions that I could choose? I could choose a unit vector along the line of contact. I could call that as a direction E2 or something. Then obviously I need to have an orthonormal basis, so I can say that this is some E3, so that the E1 vector, which is the cross product of E2 and E3, is going to be at this instant in time aligned with the E1. At the next instant in time, this is going to be my E2. My E3, E1 is going to be somewhere else. Okay, so it's going to be perpendicular to that. But my E3 is always going to be along the z direction. Is this confusing to you? Are there any questions? Can you visualize this? I have a line on the xy plane. This line is rotating about the z-axis. So all I'm doing is I'm taking 3 toothpicks, aligning one of the toothpicks with the E2 direction, which at this instant in time is along the y, but at the next instant in time that can change. Which means that if I am having these 3 toothpicks perpendicular to each other, one of them is along the line of contact, the other is perpendicular to it but on the xy plane, the third one is aligned with the z-axis itself. So that's my second coordinate frame. Okay, so I'm going to call that as the frame F2. So I'm going to come from a figure here. So this is frame F2, E2, E3, E1. This frame is aligned with the x and y axis at this instant in time, but they will keep rotating. That's frame F2. Angular velocity of frame F2 relative to frame F1 is omega in the z direction. Omega F2 makes sense to everybody? I'll set it up and then we'll come back and complete this problem very quickly in our next class. One more frame, which is going to be attached to the body of the cone. And that's going to be a frame that I'm going to say is passing through this line here, this point O contacting or joining the line P. So there's, I'm going to call it by the direction n hat, that's a unit vector. If that's n hat, then perpendicular to that is m hat. N hat is piercing through the radius of the cone, and I'll maybe draw a better picture here. N hat and m hat. So n hat is maybe I should draw these dotted lines. Does this make sense to everybody? Then the third direction, at this instant in time, it's going to be what? It's going to be aligned with E1. Right? It's going to be parallel to the face, on the plane of that face. So that's going to be some direction S hat. Okay, so that's some direction S hat, which is the same as E1 hat, which is the same as the I hat at that instant. And I'm going to call this as omega body. This is B, capital B, sorry, not omega body. This is the body frame. And the whole ball game here is very last line, and then I'll leave you at that. Omega B with respect to the fixed frame F1. What is this going to be? And what we are going to do is we are going to make use of the addition of angular velocities. Okay, we are going to say that omega B with respect to F1, so omega B with respect to F2. This is the point. So next lecture, I'll come back. We will start off with this particular figure. If you have any questions, I have office hours on this Friday. Feel free to stop by, and if you want to know more details on this problem. If you want me to draw a better figure and notability, that's something I can do during office hours. We come back on Tuesday, start with this figure, exercise the equations that we have seen so far, and then we will move on to what is called as differential geometry, which is the Freyne-Serre frame of reference. Okay? Thank you. And as I indicated,